Hi, and welcome back to Blockchain Fundamentals with Bill Laboon. Today, we're going to discuss decentralization. So let's review the level of cryptocurrency that we have achieved in the previous lecture with ScroogeCoin. So ScroogeCoin allowed us to use public key cryptography, just like GoofyCoin, and a blockchain validated by Scrooge, that is a centralized validator, to have a very basic but also very functioning cryptocurrency. But as we already indicated, we had a weak point, specifically Scrooge. Scrooge generated all the coins. He could punish users by not adding transactions to the blockchain. He could hold the entire system ransom by refusing to update. And even if he wasn't malicious, he's still a central point of failure. What if he just forgot to publish one day? Or what if he decided that it was time for him to retire? Or somebody decided for him that it was time to retire? There was one centralized place where the system could fail. So could we take the benefits of ScroogeCoin, that is the ability to avoid double spend attacks, but without bringing in a centralized party? So the answer, of course, is yes, or at least it shouldn't be too much of a surprise if you know that Bitcoin and related blockchain technology is decentralized. So we'll make a few simple attempts at this and see what other trade-offs are made to achieve decentralization. There's never a free lunch. By trying to decentralize, we're actually going to bring in some additional problems to our systems. So let's think, why would we want things to be decentralized versus centralized? So in any system, there's always going to be a centralization between, a tension between centralization and decentralization, because there are benefits and weaknesses to either direction that you go in. And this isn't just in cryptocurrency. Or even just technology in general. We see this in a lot of different locations. So for example, the Apple ecosystem is very centralized, but it means often that new or perhaps controversial software can't be sold in their walled garden. The Android ecosystem is much more decentralized, and many more different possible projects can go on it. But this also means often that the quality isn't quite as high, and there are so many possibilities out there that you don't know what is the correct version. If we think back in history to the Roman Empire versus Greek city-states, where the Roman Empire was very centralized in Rome and was thus very powerful, but the Greek city-states were very, very decentralized, had a lot of different possible ways at looking at things. They tried different things, but they were much weaker militarily compared to Rome. Mainframes versus personal computers, where we have a lot of power in one location, but it's centralized. People may not have the ability to access those computers, versus having a lot of different computers individuals own, but aren't nearly as powerful as a mainframe. So everything in software is a trade-off, and most systems are a hybrid. So even in blockchain, what we're going to see is that the system isn't as decentralized or distributed as it could be, but there are some trade-offs to having some level of centralization in most blockchains. But Bitcoin was designed to be as decentralized as possible while still providing a cryptocurrency which worked and protected against things such as double spend attacks. If we look back to the original Bitcoin white paper, we see that it was designed to be a purely peer-to-peer version of electronic cash without going through a financial institution. And in fact, Satoshi Nakamoto, the writer of the original Bitcoin white paper, noted that our original solutions, digital signatures, provide part of the solution, but the benefits of a cryptocurrency are lost if we still require to trust a third party. So, Satoshi Nakamoto thought about what are the kinds of things that we need to do in order to decentralize. If we don't have a single person or entity in charge of the ledger, who maintains the ledger? Who has authority to say whether or not a transaction is valid? Where do new Bitcoins come from? Who determines how the rules of the system change? And how do we determine what the value of a particular Bitcoin is? So, as I mentioned, Bitcoin is meant to be decentralized, but there really are different levels of centralization. The network itself is very decentralized. If you would like to spin up your own fully validating node, it is relatively simple. Anybody can do it and join the network. Mining, it turns out, is actually somewhat centralized. We'll discuss more about what miners are doing, but they're the ones who generate new blocks in the Bitcoin network. It's open to anyone. You can even use your personal computer to start mining. But it is extremely difficult to do profitably, and there are extremely large economies of scale. So what we see is that there are only a few very large miners in the world that provide a majority of what's called the hash power, or attempts to generate a new block in Bitcoin. Updating the protocol, writing new software, this is generally pretty centralized in practice. The vast majority of nodes use a particular implementation of Bitcoin known as Bitcoin Core. Anyone can write their own node software, and there are some alternatives. For example, Bitcoin J, which is written in Java, Libitcoin, BTCD, which is written in Go, Bitcoin Knots, which is an alternative implementation. But the vast majority, by which I mean probably over 98 or 99%, use Bitcoin Core. So we have a very decentralized number of nodes. Remember I said anyone can spin up a node. You can spin up a node on your home computer relatively easily. So how can this amorphous, no need for identity to join group of nodes come to a consensus? So we need what's called a distributed consensus protocol. Right? So we have n nodes, where n can be any number. And actually this number can fluctuate as some nodes go offline, or some people decide they don't want to run a node, new people decide that they do want to run a node. And some of these nodes may be faulty. They may be providing invalid data, or spamming the network. There's some may be even malicious. That is, they're intentionally trying to harm the Bitcoin network. So a distributed consensus protocol that would allow us to come to a consensus between all of the honest nodes has to have a few different properties. It must terminate, that is, running this algorithm must end with all the honest nodes in agreement about what is the value, what is the particular ledger that we agree upon. And that value must have been generated by an honest node, even though there are faulty, malicious, or non-responsive nodes that are also on the network. So here is how Bitcoin gets around that. So a Bitcoin network is a peer-to-peer system. So just think of it as a mesh of nodes in a network. Alice wants to send Bob 1 Bitcoin. So she writes a message, pay the public key of Bob 1 Bitcoin, signs that message, and transmits it into the network. All of the nodes in the network, once they hear about that transaction, will tell other nodes that they're connected to. And it will eventually filter to the whole network. Every node in this network, a fully validating Bitcoin node, is going to have a copy of the blockchain up to that point of time, as well as a list of any outstanding transactions that it knows about. So this is called the transaction pool or mempool. All of these transactions that are just waiting to be put into the official blockchain. The initial node that it gets sent to is going to gossip amongst all of the other nodes that it knows about to tell them about this transaction, as long as it's valid, and add it to their transaction pools. So the blockchain is going to be relatively equivalent across all of these different networks, modulo some network time to propagate it. But what we're going to see is that the mempool is going to vary dramatically from one system, one node to another. So different nodes may have very different transaction lists. So imagine Alice and Carol have both done transactions, but in different parts of the world. Well, one node at one end of the world may know about Carol's transaction, but not Alice's, whereas another node may know about Alice's transaction, but not Carol's. Okay. So what we want to do is determine, all right, which transactions are we going to put into the blockchain? Since there's going to be different nodes that are going to have different ideas of what transactions are out there, we're going to need to come up with some consensus mechanism to determine which transactions should be put in the blockchain. So in our naive example might be every 10 minutes, we're going to use some like voting mechanism to determine, all right, which transactions are put in the blockchain. We'll all vote on which ones, every node is going to vote on which one is valid and which one is not. But there's a problem with this very naive consensus protocol of just voting on if more than 50% of our nodes have a transaction and considered valid, we put it in. The first off, there's no real notion of universal time. Who decides when it's been 10 minutes? Different computers may be slightly off in terms of time, and so there's no way to have a universal network-wide decision on what exact time it is. Which specific consensus mechanism do we use to vote on this? The network is imperfect. You may have a fault in the network. You may have a system that's not responding. You may not know exactly how many nodes exist at a given time. So we could keep track of that, about which nodes are known to exist to the system, but that just brings us back to having some sort of centralized entity in charge of all of that. Malicious users could spam the network. They could send invalid transactions simply to chew up CPU. So there are a lot of problems with our generic naive consensus protocol of just voting to see which transactions go into the blockchain. It turns out that this issue of having to have a large number of nodes that have a limited amount of ways to communicate, some of which may be faulty or even malicious, is a problem that the computer science world has referred to as the Byzantine generals problem. This goes back to the canonical explanation of the problem, which is you have a variety of generals who wish to attack a city. And those generals must all decide what time to attack. But when they're sending their messages, other generals who may be traitors could modify the messages. So how can we come to a conclusion of when we should attack the city if some percentage of our generals may be traitors? Similarly, coming to a consensus in Bitcoin or any other decentralized ledger technology, we need to have a way to determine what is the consensus amongst all the honest validators. The problem with doing this is what's called Segal's law. A man with a watch knows what time it is, but a man with two watches is never sure. What we mean is that all of these different nodes are going to have to come up with conclusions on their own. There's no centralized mechanism of time control. There's no way to say that X event happened before Y event. And once you've removed that ability to have do X and then Y, it turns out that a lot of algorithms used for determining the correctness of an event are not really feasible. One of the particular ways that our consensus can fail is through something called a Sybil attack. So remember, we thought about having votes. Our nodes would vote on which transactions to include. So we have 16 nodes. So in our example, if 9 nodes say that a transaction is valid, we would add it to the ledger. But what if Eve creates 25 malicious nodes and adds them to the network? So Eve is pretending to be multiple entities. That's why it's called a Sybil attack. It's actually based on an old book and movie about a woman named who had multiple personalities, one of whom was named Sybil. So in this Sybil attack, Eve creates more nodes than there are honest nodes in the network. So she can always vote against adding any particular transaction or adding a particular transaction as valid because she has more nodes. So if we just vote based on the number of nodes, and nodes are relatively easy to set up, we are at risk of this Sybil attack. So let's come up then with a simplified version of what Bitcoin uses as its consensus algorithm. So our new transaction is broadcast to all nodes. Each node is going to collect new transactions into a block. And in each round, some random node gets to broadcast its block. So of the n nodes, a random node is going to broadcast its block. So we are assuming here that we can avoid these Sybil attacks, but even if Sybil does have a large number, if Eve has a large number of these nodes, the worst that can happen is she would just generate a transaction that's invalid or that doesn't contain any transactions. Everyone else would know about these transactions, and as soon as a valid node is selected at random to be the next block producer, then they can do that and include any transactions that Sybil missed. The other nodes will accept the block if and only if all the transactions in it are valid. Remember, Sybil cannot generate new transactions. You would need to know the secret key of the owner of the coins to send a transaction. Nodes will express their acceptance of this block by including its hash in the next block. So basically generating a hash pointer from their newly generated block to the previous block that was generated by the previous node, the previous selected node. So here we have a graphical representation of that. Recall that all nodes have a copy of the blockchain. So this is, as a side note, one of the other problems with a decentralized technology is that every node is going to need a copy of the blockchain, which can be tens or hundreds of gigabytes. So you can imagine that storage space, it's going to use up a lot more storage than if something were centralized, even if you included a few backups. The Bitcoin full blockchain, for instance, last I looked, was stored on at least 10,000 or more actively running nodes. So here, the red node was picked at random of all the known nodes that are out there. It packages all valid transactions into a block and adds it to the blockchain. It then broadcasts the new block, thus the new blockchain. And other nodes adds red's block with the new version of the blockchain with the new block and hash pointer. But you can see a few problems here. How do we know what are all the nodes that are on the network? What percentage of them are there? There are actually some solutions around this, and we'll see some of those when we talk about proof of stake next lecture. But at a simplified level, we can see that this is going to cause a few different problems. One is that any individual node now has, that was selected, has power. For instance, red here was selected but doesn't like Bob's transaction for one reason or another. So red packages all the valid transactions into a block, adds the valid block to the blockchain, which does not have Bob's transaction, and broadcasts the new block and thus new blockchain out to the world. Other nodes are going to add red's blockchain, and now Bob is not going to be able to have his transaction confirmed. Perhaps some other nodes have a copy of his transaction, but if enough different nodes are trying to blacklist Bob, then it may be a while before his transaction actually goes through. This also allows for double spends. So let's say Alice purchases software from Bob for 1 Bitcoin. She generates a transaction to send to Bob. An honest node now includes that block in the blockchain. So Bob sees this block has been confirmed and Alice downloads the software. So now Alice has gotten something for her token, for her coin. Then Alice's node is selected as the producer for the next block. So instead of building on block N, the one in which she sent this coin to Bob, she instead builds on block N-1. She ignores the previous block and makes her own block where the Bitcoin go to some other address she controls. So she basically sends it to herself. This transaction to Bob is now useless. The Bitcoin in that block cannot be used by him in later blocks. It's not under his control. It went to some other it went to some other address that was controlled by Alice. So let's look at that graphically. We can see how it works. So here, Alice creates a message that says, pay to the public key of Bob 1 Bitcoin. She signs it, but an honest node selects it and prints it, adds it to the blockchain. So we can see in block sub N, there is transaction sub Alice. Now Alice's node is selected. Instead of building off of block sub N, which includes transaction sub Alice, she builds off block N-1. She creates a block N sub N prime, which includes a separate Alice transaction, which instead of going to Bob's address, goes to another address controlled by Alice. Remember, generating addresses is a relatively simple process. So now when other nodes see this, they don't know, should we build on top of the blockchain that ends in block N or in block N prime? If they build off block N, then Alice's transaction has gone through. If they build off block N prime, Alice's transaction just goes to another address controlled by Alice. So we still have the possibility for a double spend here, even with our decentralized consensus. So we can protect against double spend by waiting to a number of blocks being produced after it. If we're only waiting for one confirmation, that is one particular node that may or may not be honest, then the possibility of one randomly selected node being dishonest is relatively high. But if we wait a number of blocks, well, we would need to make sure that all of those blocks are dishonest before our transaction would be erased out. So the more blocks in the blockchain since the transaction, the harder it is for someone to generate a different blockchain with different blocks. The general rule in Bitcoin is to wait 6 blocks, and blocks are generated on average in Bitcoin about once every 10 minutes. And as we'll see, generating a block in Bitcoin is extremely difficult. And so the more blocks they could put on top of that, the more work, the more difficult it's going to be to do one of these double spend attacks. So if you recall, I said let's set aside Sybil attacks for a moment because there is the possibility that a Sybil attack could mean that a transaction would not go into a block for a while. But we certainly don't want to have Sybil attacks be possible. That if we did, then we would have transactions that could be pushed off for potentially a long amount of time before they actually get into the blockchain. So in the assumption that we made earlier, we said, let's assume that at least half the nodes are honest and we're invulnerable to Sybil attacks. We know this is not true in practice. So how can we avoid that? How can we have a decentralized system that may have many dishonest nodes that has the possibility of Sybil attacks, but still avoid double spends? So in the next lecture, we're going to discuss some incentives that will help avoid that, including proof of work and proof of stake, and how mining works in Bitcoin and other proof of work systems.